which would be down to negative 63 pounds, and it would go up 16 more, up to positive 33, and that's all of it, isn't it? Because negative 63 is below negative 58, and positive 33 is above 21, so all of your data is. In reality, with larger data sets, it's close to 100, but not quite 100%. But don't get too hung up on that. We'll come back to that towards the end of the class. This is the big one. The 95% is the big one. You'll very, very often, when you read Gallup polls, Quinnipiac polls, when you read media surveys that you can actually get the raw data on, they'll talk about something called 95% confidence. That's what they're talking about. Or if you're looking at psych journals and social journals, a p-value less than 5%. That less than 5% identifies the outside of 95%. So this is the one that's used the most. 244, we talk about why it's used the most. Fair so far? Now, one of the reasons that psych and stat journals use that 95% so much is they like to compare the 5% that fall out to the 95% that are in. The 95% that are in are the typical values. And I think Tabitha hit it on the head when she said, man, if they told me that, you've got a 95% chance, basically, of losing at least 47, but maybe gaining 17. You'd be like, that's all over the board. That's not very consistent at all. And it's all relative speaking. Comparing it to a different data set, maybe it is. What weight loss programs will do is they will report, if they're trying to sell something to you, Subway was notorious, Subway and Jared. They're going to show you this data point down here. Jared lost blah, 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 blah on the Subway diet. They're not going to tell you the average weight loss is actually negative 1 pound. They're going to say Jared lost 56. While they're at the bottom saying results not typical. So in other words, they're reporting to you, come eat at my restaurant, I'm going to give you an atypical result to convince you to do it.
Like the Taco Bell diet.
Look at any of them. Taco Bell diet, weight loss programs, they're always going to show you people. They're always going to show you these people.
I don't watch TV.
Crap! But that's why you read the fine print. That's why you read the fine print. That's why you pay attention to outliers. Outliers, essentially loosely defined. We're going to have a couple different definitions of what these outliers are. Outliers, loosely defined, outside of the 2 standard deviation mark. Loosely defined. So you have 2 standard deviations. Anything above or below the endpoints of that are loosely defined to be outliers. Too big or too small. To be typical. To be typical. Is that fair enough? So I guess to answer Shelby's question, to come back to Lucas's question from before, an hour ago, this is another beautiful use of a standard deviation. It allows us to not just measure variation in an absolute, but it allows us to predict percentage-wise how much of data is going to behave in a certain way. That's pretty cool. And not only that, Tabitha, back to your question, when you said, oh my God, if they told me that negative 47 to 17, well, you have a 2/3 chance of that happening. You have a 1/6 chance, basically, of picking up more than 17 pounds. And you've got a 1/6 chance of losing more than 47. See what I just did there, friends? 100% of the data is in this bell. 2/3 is in the middle, 1/3 is in both ends. Since it's basically bell-shaped, you can assume the tails are the same size. So cut the third in half, make it a 1/6 each. So looking at it that way, 17% chance, 17% chance, 66% chance. And then again, how much of a gambler are you? Will you look for a diet program that has a smaller standard deviation, maybe the same average? We can't make those calls. All we can do is present the information and let folks interpret it. Believable? Mm-hmm. Any questions right now? That's a lot of definition today. I apologize for that. It's a bunch of definition, but this idea of standard deviations is not always super clear. I wanted to make sure we drove that point home. Cool so far? There's only one last thing I wanted to run by with you guys, and it's more a technical thing than a theoretical thing. It's the same theory that we're talking about right now, but it's how to do this kind of stuff when you don't have raw data, which you often don't have. I love raw data. Raw data is wonderful. It's great having the. I want to get Jenny's total fit results from yesterday, and do like average number of high knees over the course of for 50 seconds. It'd be great to analyze that kind of stuff. Well, maybe we will if I can get it from them. But that's when I can actually get close to the data source and pull the raw data from it. I tried to get data from energy bracelets. Have you seen these? The power bracelets. Yeah. You know, power bracelets. The ads. The ads were great. Here, dude, come here. Here's a jump. Here, stand here, jump there. And the guy jumps and they measure it. They go, come here and put this awesome power bracelet on. Nice. I guarantee this will make you jump further. Go jump. The guy jumps and it jumps like 3 feet further. You see? And I go, great. That's data set of 1. Yeah. Do it again. And they do it again. But they do it the same way every single time. Well, obviously that's crap. because it's a completely biased study. You jump without a bracelet, you tell somebody they're going to jump more, you beef them up. Completely biased study. A dude actually tested those in a controlled double-blind fashion, which means he had a bunch of randomly selected people come up, flipped a coin. If the coin came up heads, he put a bracelet on their wrist. If the heads, it was a real power bracelet. If it was tails, it was a bracelet that looked just like a power bracelet, but didn't have the whatever the hell's in the power bracelet. The energy crystal, kryptonite, whatever the hell's actually there. So half of the people, when they started, had an energy or a power bracelet on. Half people had a placebo bracelet. Then they jumped, and then he said, cool, jump again. They changed the bracelet and put the other one on there. He statistically showed there is no difference. He won't give me his data because he's trying to get it published. Good for him. He worked his ass off to get that data. But that's the trick, is when you're working on publications, they don't want to give it up. That's fair. That's totally fair. But I'm still waiting for that because I want to analyze it with you guys in class. But the fact of the matter is, even if I was to get it, chances are I wouldn't get the actual raw data of the jumps. I'd get something that looks like what is under your weight loss data there on your data sheet. Yes, perfect. Just enough time. I got Portland Marathon finishing ages. Enough talk of weight loss. Enough talk of weight loss. So this is how data often comes to you, in some kind of a grouped form. So you've got 2009 Portland Marathon. You've got ages broken down into roughly 10 or 9-year increments. Okay? So in other words, we know that there were 44 people coming over that were between 17 and 26 years old, but we have no idea how many 17s, how many 18s, how many 19s, and so forth and so on and so forth and so on. Now, we have ways of dealing with this, don't we? Yes, we've dealt with this. Basically, what we do, I'm going to erase some of this if it's okay with you guys. Bye-bye, weight loss. You've served us well. So now we'll do with Portland Marathon data. So, those folks that are 17 to 26 years of age, I don't know how many of each one we have, so how old are we going to make them all?
You're going to get the average of the two.
Yes, we do. We're going to say everybody in there is
21 and a half.
21, I was going to say 21 and a half, that's what I'm getting, 21 and a half. We're going to say everybody in there, we're going to say age. Everybody in that first group is 21 and a half years of age. Next group, 31 and a half. And so forth and so on. I should update this data with the newest Portland Marathon. There. 6 discrete ages, as opposed to however many we have in here, 60 discrete ages. And we've got frequencies. We've got 44 of those folks, 107 of those folks, 141 of those folks, 106. Who wants to remind me why the hell we can do this? Why is it okay to, they're all 21 and a half. Maybe not singing like that.
Because they tell you the frequency, but they're not giving you the exact ages. So
Totally.
It could be anything, so you might as well take the average.
Why? Why not? Why is it legal-ish mathematically to take the average? I love that statement right there. That's okay. Who remembers? It's not the easiest thing to recall. Tammy?
It's the square thing, square root.
That's exactly what it's tied to. It's tied to the fact that, yes, there are 44 people in that age group from 17 to 26. Chances are they're uniformly spread throughout that interval. So by saying 21 and a half is the average age, yeah, we're overestimating for the young people, but we're underestimating the same amount for the older people, and it's canceling out and making 21 and a half. And we might be off. We may overestimate a little bit in this category, but guess what's going to happen somewhere down the road? We're going to underestimate. Think of your keys. Think of the keys. When we collected the keys on the first day, we compared raw data to grouped data. Our averages were within 0.2 keys of each other. Even though we had great skew, it's the law of large numbers. Cancellation happens. It's exactly what it's related to, my friend. It sums to 0, essentially. Above and below sum to 0. Nice, you got it. It's exactly the time I needed, Tim. Okay, now by hand, what we'd have to do next is we'd have to create an XF column. That times that times that.
I say boo.
Well, good, Raphael. Say boo, because we're done doing that stuff. We're going to use the TI to do it from now on. Here's what you have to do. L1, L2. You need 2 lists now. You need 2 lists. This guy goes in L1. This guy goes in L2. So take your time. Enter that in. I'll go with you.
Sorry, that was rude. I shouldn't have said
It was not rude at all. But I like making you guys do manual calculations of things just enough so that you understand the inner workings. Hearing Tammy say it's the plus or minus square root thing, cancel into 0, I understand you now know the inner workings. So we can now move past that, let technology do all that annoying stuff for us and focus more on interpretations. That's what I'm all about. That's what I'm all about. Okay, I'm going to clear out L1 and replace it with my ages. There we go. Frequencies. I know, thrilling. The temperature of this room does raise very quickly, I've noticed. Even flushing it out and halfway through tends to get warm. So much stuff on, plus lots of hot air exiting. Not you guys, mostly just Italian up here at the front. I want to take a look at this data. I want to look at it. You know what we should do every chance we get? Every data set we can, let's graph. Every data set we can, let's graph. Because it's a good idea to take a look at it to see I want to use that empirical rule, if it's bell-shaped. We got to kind of know if it's bell-shaped or not. So you can hit graph right now. The problem with hitting graph right now is you're in the wrong window. Yeah, your window's completely off of where it was before. And you can also just hit zoom 9 right now, but you're not set up right. If you hit zoom 9 right now, zoom 9, you'll get that graph. That is completely wrong. Why? What are we ignoring? What kind of data did we graph last time? What kind of data did we graph last time? Grouped or? It was bell-shaped data, but what type? Go back. You had a block of data, individual values, which we call, starts with an R. We still want a histogram. I still want a histogram passing. What kind of data was that block of text I gave you? Raw. Which means the frequency count on each data point was 1. Our frequencies are now in a list. So go back to your stat plots. Second y equals. Grab plot 1. This is all golden. Cassie, I still want to go with the histogram. Because I'm still only graphing one variable. Everything's cool except for frequency. Your frequency, we're not counting everything one time. That would mean there are only 6 people in my data list. I got to count everything L2 times. So second 2, this tells the TI, oh, I've got to look at list 2 to tell me how many times to count 21.5. Mike, you should put list 2 in yours. Where it says y, it says X and Y, I
When I'm
believe.
putting in my 21.5, it's throwing in a fraction on me.
That's okay. That's okay. What, 40,
Yeah.
43 halves or something like that? Yeah, it's totally fine, bro.
Okay.
Totally fine. Cool? So make it L2. Now it'll actually graph properly. So make sure to go zoom 9 again. There she is. This makes sense with the actual data set. Yes? So are we getting success here, friends? Are we getting success? Yes? Now, one small issue, and if you can live with this, you can live with this. You see how those bars are gapped? Those bars are gapped like that. You can make the gap go away. When you press window, each of the bars right now is 5 wide. If you make that width as wide as the original width of the class, the bars won't gap. So if you change that to a 10 versus a 5, and you regraph, you'll actually, now you can say I don't care about this. You can say to hell with this, I don't mind the gap, and that's totally fine. But if the gap is throwing you off and bothering you, you can erase the gap by making them as wide as the original data was gapped. Would you call that a bell shape?
Yeah.
I would too. I would too. Would you call these folks that are out here in this last bar, which are kind of hard to see, but they're out here in this last bar, would you call those guys unusually old?
Yeah.
Would you call these guys unusually young?
No.
Okay, I didn't hear as much. I heard a lot of yeses for the unusually old folks. But the unusually young folks, I heard no. And then but I heard a pause first. So, let's quantify. Let's find the average age. Because I don't mind using an average. I don't mind using an average on roughly bell-shaped data. Let's find the average age.
Looking at that graph, they're just as old as they are young.
As they are young. But the question is, are there... Let's come back to that point, Athena, okay? I love that point. Give me 3 minutes. 4 minutes tops.
Okay.
Tops. 4 minutes tops. I want an average and a standard deviation. Sorry, that was my best Paul Schaefer interpretation. Let's do an average age and a standard deviation of the ages. Okay? All right, here we go. So we're going to go back to stat, calc. It's still 1 bar stats. Because there's only one variable I'm measuring. What's the variable I'm measuring with this data?
Average age.
Their ages. That's all I want is their age. I know it seems like it should be two because you have two lists, but it's only one list of data. So what you're going to do is you're going to grab one of our stats. Don't press enter right now. Well, what the hell? You can. But it gives you the wrong data. This is averaging only L1. Look, you can tell you're wrong because it's saying there are 6 people in your data list. Now you know there are more than 6 people. There are hundreds of people in there. So what you have to do is you've got to grab one of our stats, L1, comma, L2. This tells the TI, okay, Mr. or Miss TI, L1 is where my data is, L2 is where my frequencies are. Comma is the button above 7, my friends. Yeah, comma's got its own button. Right above 7, right above 7.
Wait a minute. Oh.
Right above 7. Oh, it's J on alpha lock. Just don't press alpha first. Fair enough? All right, let's hit enter. How many people are in this sample?
448.
Nice, friends. Hundreds are in this sample, which makes perfect sense. If you add that up, you get 448. What's their average age?
42.
About 42 years.
It's kind of old to be running a marathon.
Runners get better with age.
Really?
Runners,
Yeah,
run,
definitely.
it's amazing. Runners get better with age, especially distance runners. Especially distance runners. Yep.
Yeah, Sean kills it out there. So
Oh, I suppose I can't hang with you young people when you're sprinting.
yeah,
If I'm on a 5-mile course and I'm in my element.
then you kill it.
What's the standard deviation?
12.
Let's call that 12 years, shall we? So let's analyze this data a little bit, just a little bit. I want to answer Athena's question. It might have been coming in about 4 minutes, like I promised you. Let's set up 2 standard deviations from average, and let's call that the typical aged people in a Portland Marathon. How's that? Let's set up 2 standard deviations, because how many of the runners are going to be within 2 standard deviations?
2/3.
2 standard deviations.
Oh, 95.
95%. Tabitha, 2/3 would be how many standard deviations? 1 standard deviation. 2/3, 68% will be within 1 standard. 2 standards will be 95%-ish, roughly on average. So, 2 standard deviations, X bar plus or minus 2 S's, that's going to be 42 years plus or minus 24 years, right? So that means we're going to have down to, what is that, 18 years? Up to and including 66 years? Did I do that right?
Yep.
So in other words, anybody over the age of 66, by this definition of outlier, I can't say that enough either, by this definition of outlier, is considered unusually old, and anybody under the age of 18, unusually young. I'm not saying this disparagingly, I'm just saying by definition of the behavior of the data. So when I asked earlier, and I asked, are these folks down here, or up here I should say, unusually old, and you all went yes, well you almost had an intuitive feel for that, didn't you? Because that group is the 67 to 70, what it was, 76, which is all over 66 years. So you almost had an intuitive feel for that. The trickier one, and as rightly so, was the young one down here. Are these unusually young? Well, I heard some whales and some pauses. It's hard to say. It says that 18 is kind of the normal cutoff. Some of those kids were 17. So some of that group actually is considered too young. 95% would be roughly here. Roughly here, right? There's your 95%. So yeah, you've clearly lopped off these folks, but you've lopped off like maybe a tenth of these folks. And that adds up to your 95, or your 5% that's outside of your 95%. So really, that data example was just to make sure you guys know how to deal with grouped data. So basically, it's just making sure you let the TI know it's L1 and L2 versus just L1. Cool? Same argument applies, though. Yeah? How do we feel about this? Good? There's only 2 data sets today, but at the same time, I like just getting in there and looking at them in every possible way we could. All right, I will see you guys again till Monday. I will miss you dearly.